Let's start chapter 2 with the definitions of position, distance, and displacement. So in physics, the terms position, distance, and displacement have specific meanings. Okay, so let's talk about what is the difference here. To define the position, we need to set up a coordinate system at first. So that defines the location of our particle. So the location is its position. For example, if I'm talking about one dimension, then I can just have my coordinate system to be the x-axis. So the origin of this axis is x equals to 0, and then an arrow can point in the positive direction. This means that, for example, our particle is moving in the positive direction. So this means that the x is increasing. So if it is moving in the positive x-axis, then it means that x is increasing. When we want to set up a coordinate system, we are free to choose the origin and the positive direction as we like. But once we make a choice, then we must be consistent with it throughout any calculations that follow. Now, for example, the particle that I'm going to choose is a person who has moved to the right from an initial position. So let's say that x equals to 0 is my origin, and then I'm going to locate my person at the initial position, let's call it x sub y, and then this person is moving to the right from an initial position to a final position. Let's say that he moves here to xf. So this is the final position of my person. Now, because the positive direction I set it up to be to the right, then it follows that xf is greater than xi. Okay, so it is totally your liberty to how to choose your origin and how to choose the positive direction. But once you choose it, you have to stick with it. Next, let's define distance. Now, you know how to set up a coordinate system. So let's use the same coordinate system to investigate a situation here. Suppose that you leave your house and drive to the grocery store and then return home. Now, the distance you have covered in your trip is, let's say the grocery store is 4.3 miles away from your home. So you go to grocery store and then you come back, right? So you have covered 8.6 miles on your trip. Now, distance is defined as the length of the trip. So I can define distance to be total length of travel. All right. So because it is distance, again, the SI unit for distance is meters. Okay. So if I want to convert 8.6 miles to meters, then I just need to multiply it by, remember the conversion factor? So 1609 meters per 1 mile equals to, and I hope that you have got time to go over that supplementary video that gives you some practice on the conversion of the units. So it's going to be 1.4 times 10 to the power of 4 meters. Now, when it comes to your car, the distance traveled is indicated by the odometer, right? This is where you can see the mileage that you have traveled. Now, distance is always positive. So this is another thing that we need to know, so that this guy is always positive. Now, this is a scalar quantity because there is no direction associated with distance. So it is always positive and it is a scalar quantity. Another useful method to characterize a particle's motion is in terms of its displacement. And I'm telling you that this is the most common characterization that we use for the particle's motion. Okay, so we show displacement by delta, which shows the change x. So this is simply the change in position. What does that mean? This means that the displacement is equal to the final position minus the initial position. So final position minus the initial position. Okay, so again, this has the unit or the dimension of length. So the SI unit for it is meters. So how is this different from the distance? Okay, displacement and distance are actually really quite different. For example, in the round trip, so let me write here, in the round trip from your house to the grocery store and back, the distance that you traveled was 8.6 miles, right? But the displacement is 0. The displacement delta x is 0. Why? Because delta x was your final position minus your initial position, and because you're back to the same position, so actually the distance that the displacement is 0 for you. Let me make an example here for you. For example, suppose you go from your house to the grocery store. So you want to go from your house to the grocery store and then to your friend's house. So you go to your friends and have a stop there. Okay, now let's find what is the trip distance here and what is the displacement here. So I'm gonna sketch, remember step 1. So this is my origin, which is your house. And then let's say your xi is the grocery, and then your xf, which is final destination, is your friend's house. Okay, so the total distance that you have traveled here, so it's like you have gone 2 meters to the right and then 1 meter, so total of 3 meters, right? If we imagine, or if we assume that the initial x is 2 meters and the final x is 1 meter. So these are totally just imagination. But then it happens that your displacement delta x is x final minus x initial. So delta x is going to be 1 meters minus 2 meters. So negative 1 meters. So you can see that the displacement can be negative while distance is always positive. With all this explanation, I want you to go ahead and read the example 2.1 on page 21 of your textbook. The next step in describing motion is to consider how rapidly an object moves. For example, how much time does it take for you to go to grocery store? Okay, How fast does an orbiting satellite travel in 1 hour? So these are all examples of some of the most basic questions when we are talking about motion. So let's just define the average speed here. So this is the simplest way to characterize the rate of motion. We define the average speed to be distance divided by the elapsed time, and that is equation 2.2 on your book. Now the dimension of the average speed is distance per time, so it's going to have the dimension of meters per second. So remember that because the distance is always positive and time is always positive, so the average speed is always positive. Let's solve example 2 on your book. It says a dog trots back to its owner with an average speed of 1.40 meters per second. Okay, so remember that we need to write down the known and unknown of the problem. So I can write down that the average speed is 1.40 meters per second from a distance of 2.3 meters, and then the distance is 2.3 meters. How much time does it take for the dog to reach its owner? So this is the known, right? And the unknown of the problem is time. How much time does it take? Okay, as we talked beforehand, like we need to have a sketch. So let me just draw this cute. I'm trying my best, guys. Doesn't look like a dog, but okay. Well, kind of my dog looks like this. Okay. So this is the dog and this is the owner. Another thing that I'm going to do is that I'm going to label my sketch. Okay, so instead of just constantly writing distance, I'm just going to write D here. So this means at a distance. And then the dog is, as the problem says, trots back to its owner. So it's going toward the owner. So with the velocity or with the average speed of v. So remember that we show the speed or the velocity, both of them with v. Here, I'm going to write it here, v. All right, so now I need a good equation or a proper equation for it. So here is the equation that I have. So I know that v, which is average speed, equals to distance divided by time. Okay, now I need to find time, so I need to manipulate this equation here. So what I'm going to do is that I'm going to multiply both sides of the equation by a t. Okay, so if I do that, then I get t v equals to d, right? Because these two cancel. And because I want to find t, again, I need to have t alone on the left-hand side. So what I'm going to do is I'm going to divide both sides of the equation by a v. Okay, so then my time is distance divided by the average speed. Now that I have a proper equation, now I can go ahead and just replace the numerical values. So the time is going to be the distance, which is 2.3 meters, divided by average speed, which is 1.40 meters per second. Okay, if you use your calculator, then 2.3 by 1.4 will give you 1.6. See how the meters here cancel and the second comes up, and as we were expecting, the unit of the time is seconds. So the answer is t equals to 1.6 seconds. Now, this is exactly how I want you to solve the problems when it comes to your homework. Remember how I told you that the speed is different from velocity, although we show both of them, but the difference is that the speed is the scalar quantity and velocity is a vector, meaning speed does only have magnitude, but velocity has both magnitude and direction. Now, when it comes to average velocity, we define it as the displacement divided by the elapsed time. So the average speed was the distance divided by the time, but the average velocity is the displacement divided by elapsed time. I can show it just by writing v, and then I put this sub av, which means the average of velocity, equals to delta x divided by, this is x, delta t. So delta x is the displacement as we talked about it before. So it is x final minus x initial divided by the final time minus the initial time. Now again, this has the dimension of the velocity, so it should be meters per second for the unit. So the average velocity not only does tell us on average how fast something is moving, it also tells us the direction the object is moving. For example, if an object moves in the positive direction, then I know that x final is bigger than x initial, and the average velocity is positive. So I know that the v average is positive because time is always positive, right? On the other hand, if an object moves in the negative direction, so this is the positive x direction, but if an object moves in the negative direction, then x final is less than x initial, and I can say the average velocity is negative. Example 2.4, sprint training on your book, which is page 24, says that an athlete sprints in a straight line from 50 meters in 8 seconds and then walks slowly back to the starting line in 40 seconds. Okay, so first of all, let me just go ahead and sketch. So the first step is sketching. So I'm gonna consider this positive x-axis pointing to the right, the initial point, let's call it x equals to 0, and then my athlete will sprint. Here is the athlete who is sprinting, and then on the way back, I still consider the positive x-axis here, but then he is walking back, right? So here is walking. So here, this is the nose, shows that the direction of the motion. All right. So the next thing is that I need to identify the known and unknown of the problem. Okay, before that, let me just label the final distance, which is 50 meters. Here, 50 meters. So for the sprinting part, I know that the x initial is at 0 meters. The final location of the athlete is at 50 meters. Let's just say that he starts the motion at 0 seconds and then he completes the 50 meters in 8 seconds. This is what the problem tells us. Okay, so what it asks us is that what is the average sprint velocity? So what I don't know here, the unknown, is the average sprinting velocity, right? Okay, so the only thing that I need to know here is a proper equation, and I have the proper equation to be V average equals to delta X divided by delta T, and then I can just expand this and write it to XF minus X initial divided by T final minus T initial, right? Okay, now substitute the numbers here. Have 50 meters minus 0 divided by 8 seconds minus 0. So this is 50 divided by 8, which gives me 6.25. And again, units, units, units. Units of the velocity is meters per second. So that was part A. In part B, it asks us to find the average walking velocity. So again, my known is going to change a bit because now we're talking about his way back when he walks. So I still have X initial to be 0, X final. Okay, so here, let me go back to the other page to show you what happens here. So on the way back, because the initial point of motion is at 50 meters and then he's going back, so it's gonna be a little different. So the X initial is going to be 50. Ooh, what an ugly 50. Okay, so the X initial is going to be 50 meters and the final is going to be 0 meters. And let's just say that the T initial is going to be 8 seconds, right? So I'm going back again so that you can see, because it took him from T0 here to reach the 50 meters in 8 seconds, and then he starts from 8 seconds, and the book says that he will finish this by walking after 40 seconds. So this makes it 48 seconds here. Okay, so I can find T final to be 48 seconds, or you can just simply consider 0 for the initial and then 40 for the final. Doesn't matter. You know, the difference is this motion happens in 40 seconds. All right, so it asks us for the average walking velocity. So again, my unknown is the V average. So what I'm going to do is, again, I'm going to use the same equation, but with different X final and initial and different T final and initial. So it's going to be XF minus XI divided by TF minus TI. So it's going to be 0 meters minus 50 meters divided by 48 seconds minus 8 seconds. Okay, so this is going to be negative 1.25 meters per second. And do not forget the unit. So you see what happened here. Here our average velocity happened to be negative. It means that it is decreasing. So the rate of the motion is decreasing. And finally in part C, so it asks us to find the average velocity for the complete round trip. Okay, so here again, I have the known of this part. So the round trip, it means that he starts at 0 and then he goes back to 0, right? He's going by, it's a round trip. So he goes to 50 meters and then again go back to the 0 meters location. And then the whole trip is going to happen in 48 seconds, right? Because 8 seconds on the way back and then 40 seconds, 8 seconds on the way forward and then 40 seconds on the way back. So it doesn't matter now that what the time is, because we know that the average velocity for the whole trip is going to be 0 divided by delta t. So it's going to be 0 meters per second. So the insight that we want to have to this problem is that the sign of the velocities in part A and B indicates the direction of motion. Now, the positive means that the motion is to the right, negative means that the motion is to the left. In addition, I want you to notice that the average speed for the entire 100-meter strip is going to be non-zero. Okay, so if it was talking about the speed, it was going to be, so the speed would be 100 meters divided by 48 seconds. So if we were talking about the speed, it was going to be 2.08 meters per second. But this is the velocity, and the velocity is based on the here displacement, not based on the distance. What often is useful to us is to visualize a particle's motion by sketching its position as a function of time. So what I'm going to do is to sketch the position as a function of time. So I can write this x in meters based on t in seconds. So if a particle moves in the positive direction for 2 seconds, this means that the particle, let's say that it starts from, I don't know, 1 meters here, and then move in the positive direction, and then moves in the direction, in the negative direction, right? So I'm gonna have some graph like this. So what matters here is that if this is my point A, nope, I'm gonna put it right here, and then this is just on 3 seconds, this is my point B, and let's say that my particle at 3 seconds is at 2 meters, right? So this is 1 meter, 2 meter, and then 3 meter, and this is like 4 meter, like this. So from point A and point B, I know that the average velocity is going to be delta x divided by delta t. Okay, so it's going to be delta x divided by delta t. So this is, well, the slope of this line here. So I can say that the slope is the V average. So the slope of the line or the triangle here, the line that connects point A and point B is equal to V average because it is delta x divided by delta t. So if the particle moves in the positive direction, then the slope is positive, as you can see here. But what if, for example, if the particle goes from here to here, right? So let's call this point C and point D. Then the slope of the line is going to be negative. So here, this is the slope of the line that connects these two, right? So then here, the slope is again delta x divided by delta t, but then you know that delta x is negative, so is the slope. The take-home message is this: the slope of a straight line between any 2 points on an x versus t graph equals to average velocity between those 2 points. Now, positive slope means that the net motion is to the right, and then the negative slope means that the net motion is to the left. Well, Although the average velocity is useful to characterize motion, it can miss a lot, right? For example, suppose you travel by a car on a long straight highway covering 92 miles in 2 hours. Now, your average velocity is 46 miles per hour. Now, even so, there may have been only a few times during the trip when you were actually driving at that average velocity. Now, if you want to have a more accurate representation of your trip, then you should average your velocity over shorter period of time. Okay, so if you calculate the average velocity over 15 minutes, then you have a better picture of what that trip was like. If you can just average your velocity over 5 minutes, you can have even a better idea. In 2 seconds, 1 second, even it gives you an even better idea. So the idea of a velocity corresponding to an instant time is what is meant when we say instantaneous velocity. Okay, so mathematically, we can define that. So now I do not put that sub AV here because this is the instantaneous velocity. So mathematically, I can write the limit of delta x divided by delta t when delta t is very, very small. It means that it just like goes, or it goes to zero. So approaches the zero. This is how we say it. So in this expression, that lim means evaluate the average velocity delta x divided by delta t over shorter and shorter time intervals approaching zero in the limit. Now, this instantaneous velocity can be positive, it can be negative, or it can be zero, just like the average velocity. Now that we know what is instantaneous velocity, if we can just forget about the direction, the magnitude of instantaneous velocity is the instantaneous, did I miss an N here? I did. Okay, instantaneous speed, right? And this is what your vehicle's speedometer reads. So when your speedometer shows 60 miles per hour, that is your instantaneous speed of the car. On the graph, when you just draw the position versus time, then you get to have a just shape for this graph. So remember that between point A and B, the average velocity is the slope of the line that connects these two, right? So this is the slope is the average. But then for having instantaneous speed, what you need to do is at each point, you need to have the slope of the tangent line. So this is, for example, at t equals to, let's say this is 5 seconds, okay? So the slope of tangent line is equal to instantaneous velocity. And this is hopefully what we're going to work on when it comes to lab 1. So I'm going to give you like an instruction for lab 1 later next week, but most probably this is going to be a part of lab 1. So at this point, at 5 seconds, the slope of this line is the instantaneous velocity. All right, if I want the velocity at, let's say, here is my t 2 seconds, then the slope of the tangent line on the graph, I'm not the best drawer, I'm trying my best. So the slope of this line, which is the delta x divided by delta t here, gives me the instantaneous velocity at 2 seconds. So just as velocity is the rate of change of displacement with time, Acceleration is the rate of change of velocity with time. Now, an object accelerates whenever its velocity changes, no matter what the change is. It accelerates when its velocity increases, it accelerates when its velocity decreases. Okay, so let's talk about the average acceleration, and we show acceleration by a and again sub av. It means that I'm talking about the average quality quantity. So this is going to be the change of velocity over the change of time. So I can expand this and write it to be vf minus vi divided by tf minus ti. Okay, now what is the unit for this? It is going to be meters per second, which is the unit for velocity, divided by second. So in short, it's going to be meters per second squared. This is the unit for the average, acceleration. Okay, let's just do an example here. Exercise 2.6 on page 29. It says a certain car can go from 0 to 60 miles per hour in 7.40 seconds. Okay, so known of the problem. So it says from 0 to 60 mile per hour. So I'm going to write VI equals to 0, VF equals to 60 miles per hour. And the time is given to be 7.4 seconds. It can go, this much change is happening in 7.4 seconds. What is the average acceleration of this car? So the unknown is the average acceleration of this car. Okay, so what do I need here? I'm needing a good or a proper equation. So I'm going to use A average equals to delta V divided by delta T. But this guy here, it is not the SI unit. So first thing, I'm going to have to convert mile per hour to its equivalent SI unit, which is meters per second. So bear with me here. So I know from that table on your book is that 1 mile is 1,609 meters, and then 1 hour is 3,600 seconds. So if I want to convert 6 miles per hour to something meters per second, right? So first of all, I need to have a factor that can cancel out the miles here and the hour here. So I'm going to multiply this by 1609 meter divided by 1 miles. So here is to convert the mile. And then again, I'm going to multiply this by 1 hour divided by 3600 seconds. So this is just to get rid of the hour. Okay, now I can have meters per second. So I'm going to have to, so what is this? So it's going to be 6 miles per hour, 60 miles per hour equals 2. So you're going to multiply 60 by 1609 meters and then divide it by 3600 seconds. So it's going to be whatever is going to be, right? Let me calculate it in a second. Okay, use my calculator and I'm getting 2.81666666 and so on. But as we talked about this, the correct sig fix, I can see that my problem gives only two significant figures. So I just keep it at two significant figures. So 60 miles per hour is going to be 2.8 meters per second. Okay, now that I know the conversion, so I'm going to make it a little bold so I don't make a mistake. So I can write that the average acceleration is 2.8 meters per second divided by time. And time is 7.4 seconds. Okay, so this is a good example of just checking like if it makes sense or not. So it happens that I made a mistake and missed this beautiful 6 here. So it's actually 26.8 meters per second. 26.8. All right. So always check if your answer makes sense. Because I was like, no way that 60 miles per hour can be 2 meters per second only. Okay. So I'm going to correct this. 26.8 meters per second divided by 7.4 seconds. So it is going to be 3.62 meters per second squared. Guys, do not forget to box your final answer and write the unit. Very similar to the instantaneous velocity, will have instantaneous acceleration, and I'm going to define it to be a equals to the limit of delta v divided by delta t when delta t approaches 0. Okay, so it is kind of like the same, right? So when acceleration is constant, then the instantaneous and average accelerations are the same. So this means that if I have a graph of velocity versus time, and this is going to be in meters per second, time is going to be in seconds. So if I have like a graph of velocity versus time, so if I choose 2 points, now the slope here, right, this slope here gives me the average of acceleration. Why? Because the slope is going to be delta V divided by delta T. So delta V divided by delta T. And then if I have like a more, okay, so here because the slope is constant, so the average and the instantaneous acceleration is the same because any tangent line actually has the equal slope to this, the slope of the, like what you see here. But if you have, for example, v versus time, and then you have something like this, right? Then the average between point A and B, the slope of this line, so the slope of this line is going to give you the average of acceleration, but then the slope of any tangent line at any point is going to give you the instantaneous acceleration. So slope. So these are the slope equals to slope equals to. So this is a very similar idea to what we had for the velocity, but velocity was the slope of the line for the graph of x versus t. Now acceleration is the slope of line for the graph of velocity versus t. Let's stop here, but I let you read the example. So I'm going to write it here for you, 2.8 on your book, and then the example 2.9 on your book, and then there are some practices that says enhance your understanding. These are all on your book, and you have the whole day to study them and make yourself like practice. Again, I'm gonna like upload a supplementary um, video about this chapter for you, or this section, these sections. This is section 1, 2, 3, and 4 of chapter 2. So I'm going to upload some supplementary videos that gives you some practices on the average velocity, instantaneous velocity, the average acceleration, and the instantaneous acceleration.